Good day, class! So for today's discussion here in Mechanics of Deformable Bodies, we are going to continue our discussion about the fundamental concept of strain and deformation. So for this lesson, students must be able to draw stress-strain diagram and identify the critical points in the diagram, and students must be able to discuss the mechanical properties of materials. So let's start our discussion. Okay, so here in Mechanics of Deformable Bodies, we are actually studying the strength of a material or the ability of a material to sustain a load without undue deformation or failure. So for us to know the strength of a material, it is important that we have knowledge about the mechanical properties of materials such as strength, ductility, brittleness, toughness, hardness, no, etc. Okay, so stress and strain, they are two fundamental concepts of mechanics of materials. No, that's why we discussed first, no, the concepts about stress and strain, because we are going to use, no, their concept. No, so the relationship, no, between stress and strain, no, it defines the mechanical properties of a material. That's why the knowledge of which is of utmost importance in design. Okay, so these mechanical properties, this is inherent or integral in the material itself and must be determined by experiment. Okay, so we can determine mechanical properties, no, by conducting experiments such as tension or compression test. Okay, so this test, no, it is primarily used to determine the relationship between the average normal stress and average normal strain in many engineering materials such as metals, ceramics, polymers, and composites. So, after we, let's say we conduct a test, a compression test or a tension test, and we determine from that test the stress and the strain, no, of a material. No, so after we determine that, no, we are going to analyze their relationship, no, the relationship of stress and strain, and from that, no, we can describe or derive the mechanical properties of that material being tested. Okay. Okay, so we will talk about how a standard tension test is done. Okay, so the specimen, no, as you can see here in this figure, so this is a specimen of, let's say, a steel or any metals, no. So this specimen, it will be placed in the grips of a testing machine. So this is a testing machine, no, that we are using in a tension test. Okay, so the grips, no, of this testing machine. Okay, so these are the grips of the testing machine. These are designed so that the load P, no, the load P applied to the specimen by the machine is axial. Okay, so two gauge marks will be scribed in this specimen, and these two marks, it will define, no, the gauge length. So this gauge length, no, will be observed, no, all throughout the experiment or the test. And as you can see here, these two marks, they are actually a little bit away from the ends, no, so that local effects caused by the grips will be avoided. Okay, and also to ensure that the stress and the strain are uniform in the material between the mark. So after we place this specimen, no, here in this testing machine, okay, so continuous application of loads will be done, no, and continuous reading, no, of those applied loads will be taken, and at the same time the elongation, no, of the gauge length, no, it will be recorded as well. Okay, so the testing machine, it will elongate the specimen, di ba? And that will happen at a slow and constant rate, no, until the specimen rupture. So continuous application of loadings, no, will be done, no, to the specimen until that specimen ruptures or fails. No, so after that, no, the data that will be recorded, it will be used to compute the stress and the strain that specimen experienced. No, so to compute for the stress, no, or the normal stress, it will just be equal to the loads applied, no, at different intervals over the cross-sectional area, no, of the specimen being tested. So this is also called nominal or engineering stress, because the area that we're going to use, no, to compute this will be the original cross-sectional area of the specimen. So realize that upon application of load P, no, to the specimen, no, it will elongate. And since it will elongate, no, realize that the cross-sectional area will actually depletes, right? Or deplete, no? It will deplete. So to compute the true stress, no, of a material, no, upon application of that certain load P, no, the cross-sectional area that should be used, no, it must be the cross-sectional area at that moment or at that period. Okay, but here we are going to use we are going to use nominal or engineering stress. No, so all throughout the computation for stress, we are going to use the original cross-section area. Okay, and also we are going to compute the strain. That will just be equal to delta over L sub O. Where in delta here, no, this will be the deformation or the change in length, no, or the elongation, no, that the specimen, no, will undergo. Okay, so that will be the deformation over the original length or the original gauge length. Okay, so that will be called the nominal or engineering strain. So this recorded or computed stress and strain, no, we are going to graph this, no, and we are going to interpret, no, from that graph the mechanical properties of a material. Okay. Okay, so if we are going to graph the values of stress and strain that we computed, no, from the tension test, okay, so the vertical axis or the y-axis, it will be for the stress, sigma, and the horizontal axis or the x-axis, it will be for the strain, epsilon. Okay, so this graph, okay, so this is called the stress and strain diagram. No, so this graph here, no, that you can see. So this graph, okay, so as you can see here, so this is the conventional and true stress strain diagrams for steel. Okay, so this is for steel. So this one, okay, this is the conventional stress strain diagram, and this one, okay, this one, okay, so this is the true stress or true stress strain diagram. Okay, so from here, no, as you can see, in this region, okay, so the steel is in its elastic behavior. Okay, and from this point up to this point, the steel is in its plastic behavior. Okay, so in this region, no, so this is called elastic region. Okay, and the plastic behavior of steel, no, this is divided into the stages: yielding, strain hardening, and necking. So we are going to discuss, no, each and every stage here. Okay. Okay, so we are now going to discuss every region of this graph. Okay, so we will start with the elastic behavior. So the elastic behavior of the material occurs when the strains in the specimen are within the light orange region as shown here. So this is the light orange region, no, in this graph, and this is the elastic region. Okay, so here, the curve is actually a straight line throughout most of this region. No, as you can see here, from this point up to this point, no, so this is actually a straight line so that the stress is proportional to the strain. Okay, so again, the stress is actually linearly proportional, no, to the strain. Meaning to say, if the stress increases, the strain also increases, no, in this region. Okay, and here the material, no, in this region, no, it is said to be linear elastic. Okay, so the upper stress limit here, no, to this linear relationship is called the proportional limit. So as you can see here, this point, no, this point is called the proportional limit, and this is denoted by sigma sub PL. Okay, so if the stress slightly exceeds the proportional limit, no, from this point, no, the curve tends to bend. No, so this is no longer a straight line here, so it will cause to, or it will tend to bend and flatten out. Okay, until it reaches the elastic limit. No, so the point, no, after the proportional limit will be the elastic limit, and that point is this point. No, so here at this point, no, upon reaching this point, if the load is removed, no, the specimen will return back to its original shape. No, we already talked about this, diba, in our discussion about the introduction of mechanics of deformable bodies, that elastic materials, no, if we apply load, no, and we remove the load, no, the material will just return to its original shape. No, so that's the concept of being elastic of a material. No, so here in this region, again, if we remove the load, no, the material will just return to its original shape. So normally for steel, however, the elastic limit is seldom determined since it is very close to the proportional limit and therefore rather difficult to detect. So take note, class, that the proportional limit and the elastic limit, they are actually very, very close. Actually, even this next point, which is the yield stress, no, so these three points, no, in this graph, no, they are actually very, very close with each other. Okay, so take note, class, that in this discussion, however, we will assume that the yield stress, elastic limit, and the proportional limit all coincide unless otherwise stated. So, class, this graph is just exaggerated for us to see, no, every point here. But again, no, these 3 points, they are very, very close, no, with each other, no, in reality. Okay, so okay, take note of that. Okay. Okay, so now for the next stage, which is the yielding. So a slight increase in stress above the elastic limit. So the elastic limit is somewhere here. So that will result in a breakdown of the material and cause it to deform permanently. So this behavior is called yielding. So yielding here, no, this is indicated by the darker orange region here. Okay, so the yielding here starts here at this point. No, so that is the point next to the elastic limit. No, so if the graph, no, reaches this point, no, so yielding will already happen. No, so in yielding, no, the deformation here will be permanent already. Okay, so here, if here in the elastic region, no, the material will experience deformation, but it can still go back, no, to its original shape. Here in yielding, so this will already undergo plastic deformation, no, or permanent deformation. Okay, meaning it will it can no longer go back, no, to its original shape once it reaches this point. Okay, so from this region, no, so the stress that causes yielding is called the yield stress. Okay, so that is denoted as sigma sub y. Okay, so the yield stress, that is also called the yield point, or sometimes we call it also as the yield strength, no. So and the deformation that occurs in this region, that is called plastic deformation. So like what I've mentioned, so the deformation here, no, that happens here is already permanent, okay, in yielding. Okay, and it can no longer go back or return to its original shape. Okay, so although not shown in this figure or in this graph, for low carbon steels or those that are hot rolled, the yield point is often distinguished by two values. So this yield point, no, it can be distinguished by two values. So the first one will be, or the first to happen will be the upper yield point, no, and then followed by a sudden decrease in load carrying capacity to a lower yield point. But here, it's not, no, it's not indicated here, okay? But in some cases nga, no, there are what you call the upper yield point and the lower yield point. So notice that once the yield point is reached, then as shown in this figure, the specimen will continue to elongate. As you can see here, from this point up to this point, no, as you can see here, this is just a horizontal line, right? So meaning to say, the stress here, no, is not increasing anymore. But still, the material, no, its strain is still increasing, right? Okay, so meaning to say, the specimen will continue to elongate, no, without any increase in load. When the material is in this state, no, it is often referred to us as perfectly plastic. Okay. Okay, so when the yielding has ended, okay, so the yielding will end at this point. No, so from this point, an increase in load can be supported by the specimen, meaning to say, if we increase the load from this point, no, so the stress will increase. No, so it will cause the curve to rise continuously. Okay, so it will rise continuously but becomes flatter, no, at this part, and then until it reaches a maximum point. So the maximum point, no, so this point will be the maximum stress. Okay, and this is also referred to as the ultimate stress or the ultimate strength. Okay, and this is denoted as sigma sub u. So from this point up to this point, no, the graph or the area under that, no, this in light green region, no, this region is called the strain hardening. Okay, and then the ultimate strength is commonly used as the maximum stress that the material can carry. That's why it's very important that we know how to read a stress and strain diagram, because sometimes, no, the ultimate strength, no, or the design strength, no, we take that, no, from the ultimate strength of the material, no, from the graph. Okay. Okay, so up to the ultimate stress, as the specimen elongates, its cross-sectional area will decrease. Okay, so the elongation actually starts at the yield point, right? So from the yield point up to the ultimate stress, no, the cross-sectional area of the material will decrease. And that decrease is fairly uniform over the specimen's entire gauge length. That is until ultimate stress. Okay, so however, just after at the ultimate stress, no, the cross-sectional area, no, will begin to decrease in a localized region of the specimen. As a result, a constriction or neck tends to form in this region as the specimen elongates further. Okay, so what happens is that after reaching the maximum point, no, it will go down. No, the graph will go down. Okay, so that region, no, right after the maximum stress, no, or the ultimate stress will be called necking, that region. Okay, so this region indicated in dark green, no, so this is the necking region. Okay, so here the material, no, what happens to the material will be or illustrated here. Okay, so what happens is that right after reaching the ultimate stress, no, the cross-sectional area will begin to decrease in a localized region. So this will be the localized region. Okay, and as a result, a constriction or neck. So this is a neck, no. So what happens is that it decreases at a certain certain part of the specimen, no. So this is called necking. Okay, so here in this region, the stress strain diagram tends to curve downward. So it will go downward already until the specimen breaks at the fracture stress. Okay, so the point where the fracture stress happens will be at this point. Okay, so this point, no, so this is called fracture stress. This is sometimes called rupture stress, or also it's called rupture strength, and this is denoted by sigma sub F. So right after reaching this point, no, the material will already fail. Okay, and this is the illustration of the specimen that experienced failure. Okay, so that will be ano, no, at this point. Okay. Okay, so class, as you can see here in this graph, from this point up to here, up to here, up to this point, no? So this is the conventional stress strain diagram, as I've mentioned. Okay, so class, here, no, the other graph here, as you can see here, okay, from here up to here, up to here, no? So this is the true stress strain diagram. Okay, so class, as I've mentioned earlier, that in conventional stress strain diagram, in the computation of stress, now what we are using is the original cross-sectional area of the specimen. But actually, class, when the specimen undergoes elongation, which that starts no in the yield stress or in the yield point, no, the specimen or the cross-sectional area of the specimen will actually decrease, right? It will decrease. So if the cross-sectional area will decrease, no, if you are going to use that actual cross-sectional area or that depleted cross-sectional area in the computation of stress, that will actually cause the stress to increase even more. Right? So, class, at this point, no, I've told you that when a load is increased, no, of course, the stress will increase. Okay, but if we are going to use in the computation the actual cross-section, okay, of the specimen, okay, so it will contribute to increase the stress even more. Right? Because the formula of stress is actually P over A. Right? So if the load is increased, the stress will increase. But if the area decreases, no, if the area decreases, it will increase the stress even more, right? So here, class, the actual stress, no, is increased a little bit more because the area that we use here, class, is the actual cross-sectional area, which is the depleted or the decreased, no, cross-sectional area. That's why the stress here will be higher, no, than the conventional stress strain diagram. Okay? So, again, instead of always using the original cross-sectional area and specimen length to calculate the nominal or engineering stress and strain, we could have used the actual cross-sectional area and specimen length at the instant the load is measured. The values of stress and strain found from these measurements are called true stress and true strain, and a plot of their values is called the true stress strain diagram. Okay, so although the true and conventional stress strain diagrams are different, no, as you can see from this point, no, they became different. Most of engineering design is done so that the material supports a stress within the elastic range. Okay, so preferably, no, we are designing structures or machine according to the elastic range only. No, so that is for conservative design, no, but realize here, class, no, that the elastic range, no, for conventional stress strain diagram and for the true stress strain diagram, they are just actually the same, so there will be no problem, right? So class, in practice, no, we frequently use the conventional stress strain diagram instead of the true stress strain diagram, ha? So take note of that. Okay, so the working stress, also called the allowable stress, denoted by sigma sub allow, is the maximum safe axial stress used in design. In most designs, the working stress should be limited to values not exceeding the proportional limit so that the stresses remain in the elastic range. So that is the straight line portion of the stress strain diagram. However, because the proportional limit is difficult to determine accurately, it is customary to base the working stress on either the yield stress, sigma y, or the ultimate stress, sigma u, divided by a suitable number fs called the factor of safety. Thus, to compute for the allowable or working stress, that is just equal to the yield stress over the factor of safety, or the ultimate stress over the factor of safety. That's why it's very important that we know how to determine the yield stress and the ultimate stress in the graph of the stress strain diagram, because we will use that to compute allowable stresses. Okay, so in this figure, it shows an actual conventional stress strain diagram for a mild steel specimen. So in order to enhance the details, the elastic region of the curve has been shown in light blue color using an exaggerated strain scale, also shown in light blue color. Okay, so the elastic region part of the curve, so the elastic region part of the curve, let's say the elastic region is from here to here. So this portion, this is graph exaggeratedly, in this graph. Okay, so this is the exaggerated graph, okay, of this portion of this graph. From this point up to this point, again, this is the exaggerated graph. Okay, so as we can see here, this is a straight line from here to here. So meaning to say from here to at this point, this is a straight line. Okay, and then it reaches this point and then go down and then flatten here, or this is a horizontal line here. So we can say that at this part which is this part, this represents this part of the graph, so this again, this is just exaggerated, this graph. Okay, so this straight line, which is this straight line, okay, so this is the yielding region of this graph. Okay, so from this graph, class, we are going to determine the important points from this graph. So that will be the proportional limit, the yield stress or the yield point, and then we are going also to determine the maximum stress or the ultimate stress and the fracture stress. So let's try to analyze this graph. Okay, so we are going to trace the behavior of this graph. So as mentioned in the previous slide, so the elastic region, here will be from here up to here. Okay, so this is the elastic region. Okay, so this elastic region, okay, so it is shown here exaggeratedly in this graph. Okay, so this is the exaggerated representation of the elastic region. Okay, so this exaggerated graph represents this graph, Okay, so this is just exaggerated. Okay, so class, as we can see here, the graph is straight line from this point up to this point, right? This is a straight line. So meaning to say, if this is straight line from this point up to this point, so this point, this will be the proportional limit, and for this proportional limit, the value of its stress, will be, if we project that point to the y-axis, so this represents the values for the stress, so the value of the stress at this point will be 35 ksi, or 241 in megapascal. And also here in this proportional limit, if you're going to project this point to the horizontal axis, which represents the strain, so we can see here its value, or the value of its strain. Okay, so class, these values in light blue color, these are the values of strain for this exaggerated graph, okay, and here this black or these values in black color, so these are the values of strain for this actual stress strain diagram, Okay, so here if you're going to trace this, the strain in the proportional limit is 0.0012, and its unit is inches per inches. Okay, so that will be the value of the strain in the proportional limit. Now, after we determine the proportional limit, the next the next point that we are going to determine will be the yield point. So class, I've mentioned to you that the yield point and the elastic limit are actually ano, di ba? They are very close with each other. So we are not going to specify here anymore the value of the elastic limit, because we will just assume that that is very, very close, not to the yield point. So here, class, in the yield point here, it will be distinguished by two values. That will be the upper yield point and the lower yield point. So here, the upper yield point here will be at this point. Okay, so this point will be this point. Okay, so this point will be the upper yield point, and its value, or the stress in this point, will be 38 KSI. So this is 38 KSI, or 262 megapascal. Okay, and then for the lower yield point, no, so for the lower yield point, from the upper yield point, no, there will be a sudden going down, no, it will suddenly go down here, no, and this will be ano, no, this will be a straight line here, as seen here, no, in this exaggerated graph. So meaning to say, here in this straight line, no, so this is ano, no, this represents the yielding, no, the yielding of the material. So from here, no, from this point to this point, the graph, or the material will ano, will experience yielding, no. So this straight line, no, this represents this part of the graph, ha. Okay, so the lower yield point here, class, will be this point. So this is just a straight line. So up to this point, no, so this is a straight line. Okay, so here, this point this will be the value of the lower yield point, and this is actually equal to 36 KSI. No, so that is the stress, no, for that, or the yield stress, or the lower yield stress here. Okay, so that is 36 KSI, and at this point, no, wherein the yielding will end, no, the strain here, okay, as we can see here, will be 0.030 inches per inches. Okay, now continuing, no, so the specimen undergoes strain hardening, no, from the yield point, no, from here, from the lower yield point, it will undergo strain hardening. Okay, so it will go strain hardening until it reaches the maximum point, which is this point. Okay, so meaning to say, this maximum point, no, so this will be the maximum stress, or the ultimate stress. Its value will be 63 KSI, or 434 megapascal. Okay, so here, after reaching the maximum point, or the maximum stress, or the ultimate stress, no, it will begin to neck down. Okay, it will begin the graph will begin to go down, okay, until a fracture occurs at this point. So the fracture will occur at this point, no, and the value of this point, no, will be, or the stress, no, in this fracture, or in this point, no, the fracture stress will be 47 KSI, no, and the strain for this point, no, so the fracture strain, no, it will be 0. As we can see here, no, so this is 0.380 inches per inches. Okay, so this is how we we interpret, no, or trace, no, the behavior of this graph. So this will now be the values of the proportional limit, the upper yield point, the lower yield point, the ultimate stress, and the fracture stress. Okay. Okay, so we will now discuss the stress-strain behavior of ductile and brittle materials. So materials can be classified as either being ductile or brittle depending on their stress-strain characteristics. Okay, so we will start with ductile materials. So ductile materials, these are any material that can be subjected to large strains before it fractures. Okay, so take note of that ductile materials, okay, they are subjected to large strains, okay, before it fractures. Okay, so mild steel, no, as discussed previously, no, that is a typical example of ductile materials. Okay, so engineers often choose ductile materials for design because these materials are capable of absorbing shock or energy, and if they become overloaded, they will usually exhibit large deformation before failing. Okay. Okay, so there are two ways to specify the ductility of a material. So the first one is by computing the percent elongation, and the second one is by computing the percent reduction in area. So for the percent elongation, this is the specimen's fracture strain expressed as a percent. So this is just the strain, no, at fracture of the material, ha. Okay, so thus, if the specimen's original gauge length is L sub O and its length at fracture is L sub F, then the percent elongation is just equal to L sub F minus L sub O over L sub O. So this is just the strain, L sub O, L sub F minus L sub O over L sub O. This is just strain at fracture. We will just multiply that by 100%. So previously, no, in the previous slide, no, we determined the value of the strain, no, at fracture of a mild steel, no, and the value that we determined from that is 0.380 inches per inches. So this is the strain at fracture, no, and if we multiply this by 100%, no, so this will be 38%. And this percentage, no, this is the percent elongation of a mild steel specimen. Okay, and now for the second one, no, for the second one to or second way, no, to specify the ductility of a material, that is by computing the percent reduction in area. Okay, so it is defined within the region of necking as follows. So this is the formula for percent reduction of area. This is equal to A sub O minus A sub F over A sub O times 100%. Okay, wherein A sub O here, this is the specimen's original cross-sectional area, and A sub F is the area of the neck at fracture. Okay, so mild steel has a typical value of 60%, no, when it comes to percent reduction in area. Okay, so besides steels or steel, no, other metals such as brass, molybdenum, and zinc may also exhibit ductile stress strain characteristics similar to steel, whereby they undergo elastic stress strain behavior, yielding at constant stress, strain hardening, and finally necking until fracture. Okay, so some metals, however, such as aluminum, often does not have a well-defined yield point. Okay, so we discussed, no, in our discussion about the stress strain diagram of a steel, no, which is a ductile material, no, the usual behavior of its graph, okay, it starts with a straight line, right? It starts with a straight line until it reaches its proportional limit, and then it will bend a little bit, no, and then it flattens, no, until it reaches its elastic limit, which is right after that is the yield point, right? And then from the yield point, it will either go down a little bit, or just or the graph will just be horizontal, right? And that horizontal part of the graph, no, that usually indicates the yielding, right, of the specimen, no. But here there are also cases that there are no horizontal part, no, or there is no horizontal part in the graph, no, meaning to say we cannot um see in the graph the yielding, no, of the specimen. So in that case, no, it is a standard practice to define a yield strength using a graphical procedure called the offset method. Okay, so for offset method, okay, so the steps here, no, is the first one is we are going to choose a 0.2% strain. So 0.2, that is, let's say 0.002 inches per inches, no? Or millimeter per millimeter, no? And from this point on the strain axis, a line parallel to the initial straight line portion of the stress strain diagram is drawn. No? So this is an example, no? Where we can apply offset method. So if we are going to observe, no, the behavior of this graph, there is no part in this graph where the yield point is well defined or well defined, right? So in this case, now we are going to apply offset method. So the first step for offset method is to choose a 0.002 strain, no? So from the strain axis, no, let's say our the value 0.002 inches per inches is somewhere here at this point, no? So what we're going to do is we are going to draw a straight line, okay, that is parallel to the initial straight line portion of this stress strain diagram. So the initial straight line portion here is this, ano, no, this line. Okay, so we are going to draw a straight line from the 0.002 offset, no, here. No, so drawing that straight line, no, it will intersect a point somewhere here. Okay, and that point, no, where this line intersects the curve, it defines the yield strength. Okay, so this point, no, so this point will be for if we're going to project that, no, to this axis, no, so the normal or the stress, no, or the yield stress or the yield strength, okay, of this curve, okay, is approximately 51 KSI. Okay, so that's how we that's how we uh, use or apply offset method for metals that don't have well-defined yield point. Okay, so now for brittle materials, so these are materials that exhibit little or no yielding before failure. Okay, so one of the examples of brittle materials is gray cast iron. No, so this is the graph of the stress strain diagram, okay, of a gray cast iron. So as we can see here, only the portion AB, no, so this is portion AB. So this is just the tension in the graph. Okay, so this is just the tension. So most portion of this graph is at the third quadrant, right? No, this is at the third quadrant. So what does it mean? What does it imply? No, so that means that the stresses here, no, since this is negative, these are negative values, no, meaning to say, no, this is in compression. The stress here is in compression, and the upper y-axis here, no, so the stress here is in tension. Okay, and then since this graph is in the left side, no, of the x-axis, so meaning to say the strain here is not elongation. Okay, these are negative values, meaning to say this strain are compression or contraction. Okay, so this is the this is the difference of brittle and ductile materials. So if in ductile materials, no, so the graph, no, is in the tension side. No, here in brittle materials, most portion, okay, of the the graph of the stress strain diagram, okay, is in the compression portion. Okay, so here, no, the fracture happens at point B, no, at this point. So this is 22 KSI, no, approximately. So it took place initially at an imperfection or microscopic crack, and then spread rapidly across the specimen, causing complete fracture rather. So since the appearance of initial cracks in a specimen is quite random, brittle materials do not have a well-defined tensile fracture stress, unlike in ductile materials, no. So instead, the average fracture stress from a set of observed tests is generally reported. Okay, so a typical failed specimen is shown in figure 310A. Okay, so this is the usual failed specimen, no, for brittle material. So as you can see here, there's no necking that happened here, right? So that is just for for ductile materials, no. So here, this is the tension failure of a brittle material, no. Okay. Now for compression, no, so for brittle materials, compression causes material to bulge out, no. So it will bulge out. Okay. Okay, so compared with their behavior in tension, brittle materials such as gray cast iron exhibit a much higher resistance to axial compression. So its tension behavior, as you can see in the graph of the stress strain diagram of gray cast iron, this is just no, this is very small, no, compared to the compression behavior, no, of the graph of its stress strain diagram. So it is evidenced by portion AC. So this is portion AC. So this is in the third quadrant. So meaning to say, no, the stress strain from the stress strain diagram of this gray cast iron, no, it exhibit a much higher resistance to axial compression. Okay, so for this case, any cracks or imperfections in the specimen tend to close up, and as the load increases, the material will generally bulge or become barrel-shaped as the strains become larger, as shown in this figure. Okay, so the material will bulge out, no, because of compression. Okay. So just like gray cast iron, concrete is also classified as a brittle material. Okay, and it also has a low strength capacity in tension. Okay, so the characteristic of its stress strain diagram depend primarily on the mix of concrete such as water, sand, gravel, and cement, and the time and temperature of curing. So a typical example of a complete stress strain diagram for concrete is given in the figure. Okay, so this is the stress strain diagram for concrete. So from this graph, no, by inspection, okay, we can say that the maximum tensile strength, okay, of concrete is located here, is found here. Okay, so this point, okay, so we will say that this is the maximum tensile strength, okay, of the concretes, and this is approximately 0.4 KSI. Now, for its maximum capacity in compression, okay, or maximum compression, compressive strength niya, no, so its value, no, if we are going to um, trace this graph, no, from here, so this is the maximum point for compression. Okay, so the stress here, the corresponding stress here is approximately 5 KSI. Okay, so from here we can conclude, okay, that in concrete, no, its compressive strength is 12 times greater, no, than its tensile strength. Okay, so it's really stronger, no, in compression than in tension for concrete. Okay, that's why this is the reason why concrete is almost always reinforced with steel bars or rods whenever it is designed to support tensile loads. Okay, so it can be generally stated that most materials exhibit both ductile and brittle behavior. Okay, so for example, steel has brittle behavior when it contains a high carbon content, and it is ductile when the carbon content is reduced. Also, at low temperatures, materials become harder and more brittle, okay, whereas when the temperature rises, they become softer and more ductile. Okay. Okay, so let's proceed now to Hooke's law. As noted in the previous section, the stress-strain diagrams for most engineering materials exhibit a linear relationship between stress and strain within the elastic region. Okay, so that's the usual behavior, right, of a graph, no, of a stress-strain diagram, okay, of most of engineering materials. It starts with a straight line. Okay, so that implies the linear relationship between stress and strain. So consequently, an increase in stress causes a proportionate increase in strain, meaning to say, when the stress is increased, no, the strain will also increase, and that increase will be linear. Okay, so that will be linear. That's why it's a straight line. Okay, so this fact was discovered by Robert Hooke in 1676 using springs and is known as Hooke's law. Okay, so it may be expressed mathematically as sigma is equal to E times epsilon, wherein sigma here is the stress. Okay, E here, this is the modulus of elasticity. Okay, and epsilon here is the strain. So again, here, E represents the constant of proportionality, which is called the modulus of elasticity or Young's modulus. So this is a mechanical property of a material, no, that we have to know, no, modulus of elasticity. So this is named after Thomas Young, who published an account of it in 1807. Okay, so the equation sigma or stress equal to modulus of elasticity times strain actually represents the equation of the initial straight-lined portion of the stress-strain diagram up to the proportional limit. Furthermore, the modulus of elasticity represents the slope of this line. Okay, so slope is rise over run, right? So if you are going to compute for modulus of elasticity, that is just the normal stress. So the stress, that is the rise, and then over strain is the run, right? So furthermore nga, no, the modulus of elasticity, that is the slope, no, of the line. So that's how we compute modulus of elasticity. That is just stress over strain. Okay, and that stress and strain, that is in the straight line portion of the graph. Okay, the corresponding stress and strain values up to the proportional limit. Okay. So since strain is dimensionless, from the equation sigma is equal to E times epsilon, E, okay, it will have the same units as stress such as PSI, KSI, or pascals. Okay, so as an example of its calculation, consider the stress-strain diagram for steel shown in this figure. Okay, so here, if you are going to solve for the modulus of elasticity, okay, of this steel, okay, so we are going to use, no, the value or any values of stress and strain, okay, from the straight line. Okay, that is the straight line here starts from here up to the proportional limit, right? So we can use any point, no, in this straight line, no, and then get the corresponding stress and corresponding strain, no, and we are going to use that, no, in the formula. So the formula here, okay, for solving for the modulus of elasticity is just equal to the stress over the strain. So in this case, the point that we're going to use, no, will be this point, no. So this is the proportional limit. Okay, so the proportional limit, its corresponding stress is 35 KSI, and its corresponding strain is 0.0012. Okay, so we are going to use that in our formula. So this will just be 35 over 0.0012. So solving that in our calculator, 35 over 0.0012. So that is actually 29,166.67 KSI. Or approximately, it's also equal to 29,000 KSI or 200 gigapascal, okay, or GPa. So this modulus of elasticity, this is actually the common modulus of elasticity that we use for steel, in computation for steel. No, so you will encounter this value, no, oftentimes, no, in your design calculations or computations, no. Okay. It should be noted that the modulus of elasticity is a mechanical property that indicates the stiffness of a material. So materials that are very stiff, such as steel, have large values of modulus of elasticity. So as we computed no, from the previous slide, whereas spongy materials such as vulcanized rubber may have low values. Okay, so the modulus of elasticity is one of the most important mechanical properties used in the development of equations presented in this text or discussion. No? So it must always be remembered, though, that modulus of elasticity can be used only if a material has a linear elastic behavior. So meaning to say that is just the um, portion in the graph, okay, of the stress strain diagram, wherein the curve is a straight line. Okay, so also, if the stress in the material is greater than the proportional limit, the stress strain diagram ceases to be a straight line, and so equation of the Hooke's law is no longer valid. Okay. So we will discuss further no, the concept about strain hardening. So if a specimen of ductile material such as steel is loaded into the plastic region and then unloaded, elastic strain is recovered as the material returns to its equilibrium state. So the plastic strain remains, however, and as a result, the material is subjected to a permanent set. No? So in other words, if you have a material, okay, and then you loaded that material, okay, so after you unload, no, the load in that material, okay, so that material, it can still recover its ano no, its elastic strain, or that's what we call elastic recovery. But no, its plastic strain, no, it will remain. Okay, it's like for example, no, when a wire is bent, okay, plastically, no, it will still spring back a little elastically, or it will go back a little, no, in its original state, no, but when the load is removed, it will not fully return to its original position. Okay, so that's the concept here of strain hardening. No, that is due to strain hardening. No, that it will no longer go back to its original position, although it can still recover a little. It can recover its elastic strain, no? Okay, but its plastic strain, okay, it will not be recovered anymore. Okay, so as we can see here, no, that behavior, it can be illustrated in the stress strain diagram shown in the figure 314A. Okay, so from this figure, no, the specimen is first loaded beyond its yield point A to point A prime. So its yield point is here, okay, here at this point A, no, and uh, as mentioned here, no, the specimen is first loaded beyond its yield point A to point A prime. So this is A prime, no, point A prime. So since interatomic forces have to be overcome to elongate the specimen elastically, then these same forces pull the atoms back together when the load is removed, as shown in figure 314A. Okay? So consequently, the modulus of elasticity is the same, and therefore the slope of the line O prime A prime is the same as line OA. So here, class, no, as you can see, this is the original stress strain diagram, no, of the material stated here, no. Okay, so class, the material here is loaded, right, no, in this graph. Okay, so up to this point, no, let's say we consider this point A prime. Okay, so let's say the material is loaded up to this point. Okay, now if we are going to unload, no, the material, okay, we are going to upload. So what happens is that the graph, okay, it will not go back, okay, to its original graph. Okay, it will not go back to this graph. Okay, when we upload, when we unload, no, the load from the material. So the new graph here will be this graph now. No, this is from O prime, no, up to A prime, and then we proceed to up to point B. No, so this will now be the new graph. Okay, the new graph of the unloaded material. Okay, so class, this line, no, this line O prime to A prime, no, so this line is actually parallel to this. Okay, so this is the ano, no, linear elastic portion or behavior of the graph. So this is just parallel to that. No, this line is parallel to this. Okay, so this will be the new graph for this, okay? And now this line, no, of the new graph here, okay? So this is the same elasticity naman, no, with the first graph, right, or the original graph. So meaning to say, when you unload a material, no, the modulus of elasticity remains the same. Okay, however, no, the graph, no, became new here, no, that instead of the origin is here at point O, no, now the origin, okay, of the unloaded material will be here at point O prime. Okay. Now here, if the load is reapplied, okay, again, let's say we apply a load and then we unload it. Now, we reapply a load on that unloaded material. So what happens is, the atoms in the material will again be displaced until yielding occurs at or near the stress A prime. Okay, so now here, no, the yielding will happen here, no, at A prime. If here in the original graph, yielding happens here at point A, so here in the new graph, after strain hardening, okay, so now here, the new yielding stress will be, or strength will be here at point A prime. Okay, and the stress strain diagram continues along the same path as before. Now, it should be noted, however, that this new stress strain diagram, defined by O prime, A prime, B, now has a higher yield point. Now, so as a consequence of strain hardening. In other words, the material now has a greater elastic region. So as we can see here, this will be now the new elastic region, no, of the behavior of the material, no, and however, it will become less ductile. Why? Because the plastic region here will become smaller, no, than when it was in its original state. So in its original state, its plastic region is this region. Okay, so this is much greater, right, than the plastic region of the unloaded material. Right, so that will be the consequence, no, of strain hardening. It will yield, or it will make the yield point, no, of the unloaded material higher, and it will so that in other words, it will have a greater elastic region, no, and it will have a smaller plastic region. Okay. Okay, so let's proceed now to strain energy. So as a material is deformed by an external load, the load will do external work, which in turn will be stored in the material as internal energy. So this energy is related to the strain of the material and is called strain energy. So for applications, it is often convenient to specify strain energy per unit of volume. So this is called strain energy density. So for the formula of strain energy density, that is just U is equal to increment U over increment V is equal to, so this is also equal to 1/2 of stress times strain, no, or epsilon. So here, U here, no, that is the strain energy density. Increment U, that is the strain energy. Increment V, that is the volume of the material. Sigma here is the stress, and strain, epsilon here is the strain. So here, if we want to solve, let's say, for the strain energy, so that will just be 1/2 times sigma times epsilon times the volume, no, of the material, no. So that's how we solve strain energy. Okay, so if the material behavior is linear elastic, then Hooke's law applies, that is sigma is equal to E times epsilon, and therefore we can express the elastic strain energy density as, so from the strain energy density, no, from the formula, that is U is equal to 1/2 sigma over, or times epsilon rather. So this epsilon, no, we can express this, no, in in terms of modulus of elasticity and sigma, no. So for epsilon, no, in the elastic within the linear elastic behavior of the material, so epsilon will be equal to sigma over E. So substituting that value, no, in this formula, okay, so that will be sigma times sigma over E, right? So sigma times sigma, that will just be sigma squared. Okay, so this formula now, no, this formula U is equal to 1/2 sigma squared over E. This is now the elastic strain energy density. Okay. So from that, in particular, when the stress reaches the proportional limit, the strain energy density is referred to as the modulus of resilience. So from our formula, okay, so for the formula of strain energy density, that is equal to 1/2 over sigma times epsilon, right? So if the values of sigma and epsilon that we are going to use are the values, no, here at the proportional limit. So the proportional limit, that is the that is the end point, okay, of the straight line or the linear elastic behavior, okay, of the graph, no. So if you are going to use that value, okay, the stress at the proportional limit and the strain at the proportional limit, no, so that will be the modulus of resilience. Okay, so we can also rewrite this, no, 1/2 sigma PL epsilon PL, no. So we can rewrite this as, since epsilon PL, no, this point is still at the straight line, no, or the linear elastic behavior, okay, of the material, no, or of the graph, no. So we can rewrite sigma or epsilon PL, we can rewrite epsilon PL using Hooke's law, no. So we can rewrite that as sigma PL over E. No, so substituting that here, sigma PL over E, so the new formula here will become 1/2 sigma PL squared over E. So we can use either this or this one, no, in solving for the modulus of resilience. Again, modulus of resilience, class, this is denoted by U sub R, ha, so that is modulus of resilience. Okay, so from the elastic region of the stress strain diagram as shown in the figure, notice that U sub R, or the modulus of resilience, this is equivalent to the shaded triangular area under the diagram. So from the formula here, right, this is 1/2 sigma. Sigma here is this height, right? So this is that height, and then epsilon PL, this is this base. Now, so as you can see here, this is a triangle, right? So 1/2 times this one, this side and this side. So that is actually the formula, right? And that is actually also the formula for solving the area of a triangle, right? So meaning to say here, the modulus of resilience is just the area of this triangle. Okay, so physically, no, material's resilience represents the ability of the material to absorb energy without any permanent damage to the material. Okay, so that's the definition of resilience here, no, in mechanics of deformable bodies. Okay, so this is also an important mechanical property of a material, no, that we are going to use, no, in your design calculations. Okay. Okay, so another important property of a material is the modulus of toughness. Okay, this is denoted by U sub T. So this quantity represents the entire area under the stress strain diagram. Okay, so if in modulus of resilience, that is just up to the elastic limit, no, or elastic point or elastic linear behavior of the material, no, or of the graph. But here in modulus of toughness, no, so to solve for this, no, so we are going to solve for the area, no, under the entire curve, no, from the origin up to the fracture, or the point of fracture, no, of the material, no. So we are going to solve this entire area, and the value for that, no, will be the modulus of toughness. Okay, so therefore it indicates the strain energy density of the material just before it fractures. Okay, so for modulus of toughness, actually, to solve this, no, we are going to solve this, no, using it can be integration, no, but it will be a little bit complicated, the complication. So usually in solving for modulus of toughness, no, it's just ano, no, approximation of an engineer. Okay, if we're not going to use softwares, no, to calculate that area. Okay, but usually we use ano naman, computer software, no, or applications, no, to solve for that modulus of toughness or that area. Okay, so to know the modulus of toughness. But again, this is just ano naman, approximation, no, so I won't give you problems, no, in solving for modulus of toughness, because since it will just be an estimation. Okay, so the answer here might not be exact, no. Okay, so what's important here is you know that modulus of toughness, it can be determined, no, by solving the area under the entire stress strain curve, no, in the diagram. Okay. Okay, so when engineers are designing new structures, it is critical that they have access to modulus of toughness data when choosing materials. When designing a structure that may be susceptible to accidental overload, it is safer to select a more ductile material with a higher modulus of toughness, even if other cheaper materials have the same yield strength. Okay, so that is for for design of structures that are susceptible to accidental overload. No, so materials with higher modulus of toughness, it should be chosen, no, than materials with even with the same yield strength. Okay, let's say for this two materials, this is ductile material, okay, and this is for brittle material, no. So these are the stress strain diagram, okay, of these two materials. So as you can see here, for ductile material, since from the yield strength, no, it can still be subjected to a higher strain before fracture, no. Therefore, its modulus of toughness will be greater, no, compared to the modulus of toughness of brittle material. So as we mentioned, no, in our discussion about brittle materials, when they reach the yield strength, no, so just a little more strain, no, and it will easily fracture, no. So that's the no, difference for ductile and brittle material. So in that case, no, if you are going to design structures nga with susceptible to accidental overload, we are going to use ductile materials. Okay, because ductile materials, they have higher modulus of toughness. Okay. So let's try solving sample problem here. A tension test for a steel alloy results in the stress strain diagram shown in figure 3-18. So calculate the modulus of elasticity and the yield strength based on a 0.2% offset. Identify on the graph the ultimate stress and the fracture stress. So let's solve this. Okay, so for this problem, we are going to solve the modulus of elasticity, the yield strength, the ultimate stress, and the fracture stress, no, from the graph. Okay, so for the modulus of elasticity, so the formula here is from the Hooke's law, no, from the Hooke's law, this is equal to sigma over epsilon. So sigma and epsilon here, these are any values of stress and strain from the linear elastic behavior of the graph. So in this case, class, here in this graph, so this is the original graph. Okay, so this part of the graph, okay, so this part of the graph, this is redrawn here, no, exaggerately. So this is the exaggerated version of this point, from this point up to point A prime. So this is the exaggerated value. Okay, so the values for this exaggerated graph, okay, are in the blue color here, no, below. Okay, so these are the values of its strain. Okay, so here, no, we need points from the straight line, no, from the linear elastic behavior of this graph, which is this straight line. So we need to get a point, no, of wherein we are going to get sigma and epsilon. So in this case, we can use this point. Okay, so this point is actually the proportional limit, no, of this graph. Okay, so this is approximately here at this point. So meaning to say, the corresponding stress here, okay, so that is 50, and the corresponding strain here is 0.0016. Okay, so we can solve now for the modulus of elasticity using that point, no, from the proportional limit A. So that will be 50 over 0.0016. So this will be 31250 KSI. So this will now be the answer for this. Now for the yield strength, no, so we have been instructed in the problem that we are going to use 0.2% offset, no, to solve for the yield strength. So here, as you can see in the diagram, okay, so it's not obvious where you can find the yield strength, because there's no horizontal portion here, right, that is our initial clue, not to solve for the yield strength. But since it is stated in the problem that we are going to use 0.2%, so we are going to apply that. Okay, since the yield strength nga in this graph, no, it's not well defined, or the yield point. Okay, so in this case, we are going to use 0.2% or 0.002, no? So that will be 0.2%. So that point is actually somewhere here, right? That 0.002 offset in the strain axis. Okay, so that will be here at this point. So we are going to draw a line that is parallel to this straight line. Okay, so if we are going to draw a parallel line, so this will be the parallel line, and the point, okay, wherein it will intersect, no, the graph or the curve. Okay, so that will be the yield strength, or the yield stress. Okay, so if we are going to project that, no, to know the stress, that will be approximately at this point. So that will be let's say 68, no, 68 KSI. So that will now be the yield strength. Now for the ultimate stress, so obviously for the ultimate stress, no, so the ultimate point or the maximum point here is at this point. So this will be the ultimate stress, and this is approximately 108 KSI. Now for the fracture stress, so this will be the fracture stress. So this is the final point here. Okay, so this will be the fracture or where the fracture will happen. So its corresponding stress is approximately 90 KSI. So this will now be the answers for this problem. So that concludes our discussion. I hope that you learn and attain the learning outcomes for this topic. So for bonus points, please comment your name, your section, and the concept that you learned from this discussion. So it can be a sentence or two. Okay, so the first 3 students to comment, no, will receive the bonus point. So see to it that you really listen to this discussion, because otherwise your point or your bonus point will be void. Okay, so see you again, class, on our next meeting, and keep safe. God bless. Bye-bye.